A mod n plus B mod n. And if necessary, we may take another mod n. Same thing for the product. A times B mod n is A mod n times B mod n. The reason I'm putting another mod n at the end is that if I add two reminders, I may get out of Zn. And if I get out, I need to take another modulo. But if the result is in Zn, everything in Zn modulo n is itself. So any R in Zn has the property that R mod n is R. Any one of these numbers, when you take modulo or a reminder with a division with n, you get that number and the quotient 0. We also said last time something important here. Q and R are unique. So if you get an n and a, you want the quotient and reminder. The fact that they are unique enables guessing. As in, if I guess them right and I can verify them, I know those are the correct ones because there's only one Q and one R that works, right? So we've seen this. Here's an example here. What happens if I do 13 times 6 plus 4, everything mod 11? I can break this up into parts. 13 times 6 mod 11 plus 4 mod 11. Everything mod 11. Which now I can do, instead of doing the multiplication and then check the reminder, I can do first the reminder and that will be much easier because how much is 13 modulo 11? What's the reminder when I divide 13 by 11? 2. How about when I divide 6 by 11? 6 by 11? 6 is in Z11, right? So who's Z11? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So because 6 is in this set already, when I took the modulo, the reminder, I get 6. Same thing with 4, right? 4 modulo 11 is 4. So now 2 times 6 plus 4 is 16 mod 11. Now 16 is not a reminder. It's not in Z11. So how much is 16 modulo 11? Hands up to suit me. Good. This is pure mechanics. I've never seen an honor student, or actually any student, missing conceptual parts in here. But I feel essentially everyone making calculation mistakes. So I wouldn't be surprised if in quiz 3 or whatever comes next, somebody says 16 mod 11, that's 6. You know, things like that. Silly things. But I've never seen anyone not understanding how this stuff works. I can do, again, another example, 13 squared, modulo 11. I might have done this last time. This is 13 mod 11 squared, and another mod 11. Of course, 13 mod 11 is 2 squared mod 11. Now 2 squared is 4. 4, it's already a reminder, a canonical reminder how it's called, so that would be 4. The one important thing that I already said twice in here at different parts of the course, but it's a critical algorithm, is repeated squaring. So I'll just do a quick recap for exponentiation. This is an algorithm, and it's not specific to modulo stuff. It works with matrices. I show you that at Fibonacci numbers. It works with all kinds of places. The idea is that if I want, for example, 13 at 14 modulo 11, I want to calculate this. I could, in principle, do 13 times 13 times 13 times 13, 14 times. That would be a gigantic number into quadrillions. And then take modulo 11. That's hard to do. Instead, how repeated squaring works is decompose the exponent. The trick is, I'm going to write it here, decompose exponent as sum of powers of 2. So before we even start, we're going to say 13. How much is 14 in terms of a sum of powers of 2? That's the same as moving 14 into binary, right? Because in binary, the powers of 2 are the, where do I see the powers of 2 in binary? The bits that are 1, right? So who's 14 in terms of powers of 2? 8, right? Plus
4.
4 plus
2.
2. So that is 13 at 8 times 13 at 4 times 13 at 2. That's another great place to make mistakes. The plus at the exponent correspond to multiplications down, right? When we multiply things with the same base, we add exponents. So here's how repeated squaring works. First, decompose. This is part 1. The part 2 is do repeated squaring to get all, in my case, it's 13 at some power to the decay. Not just the ones I need, but all the way up. So I start with 13, modulo 11 is how much? 2. How about 13 squared modulo 11? Well, that's just the previous one squared, right? Because I already got the reminder, so I'm going to say that's 2 squared modulo 11, that is a 4. What's the next power I'm looking for here? 13 to the 2 squared. I'm squaring the previous one, so that's going to give me 13 at what power? The next power of 2, right? 4. So if I want to square the other one, that's just 4, this 4 here squared. Because I already have 13 squared. This is modulo 11. So that's 4 squared mod 11. That's 16 mod 11. That is 5. If I want the next power of 13, I'm going to have to square the previous one, 13 fourth squared. That's going to give me 13 at what power? 8. Of course, everything is mod 11, right? Otherwise, 13 to the 4th is not 5. But mod 11 it is. This is mod 11. Now, when I square things, I don't have to recompute. I just look, I already have the 13 to the 4th already, it's 5. So I just do 5 squared. Mod 11, how much is that? 25 mod 11 is 3. Suppose I want one more power. That would be 13 to the 8 squared. What power is that? 16. So that will be modulo 11, of course. I've got this 3 squared here, because I already got the 3 previously, 13 to the 8 modulo 11. So I can say this is 13 to the 8 mod 11, everything squared. 13 to the 8 modulo 11, I got it right here. Mod 11 again, might be necessary. 3 squared mod 11, how much is that? 9. Okay. How about one more? If I want 13 to power 32 mod 11, that is 13 to the 16 square mod 11. That is, I already got this 9 here. 9 square mod 11. That is 81 mod 11. How much is that? 4. Reminder to 11, that is 4. Every time you're not sure or you want to check, how do you check that you've got the right reminder? So I'm not sure 81 modulo 11. I use this equation here. What is 81 is 11, that's my n, times what's the quotient that I need there to say plus 4 at the end?
7.
Sorry. My mind is faster than my hand. 4. That's to say I have slow hands. Right? So I would recommend that to everybody doing any quiz, exercise, online homework whatsoever. When you put this reminder there, do a quick check. Who knows? Maybe you got it wrong for whatever reason. A quick check will verify immediately that that is the correct reminder. Again, they are unique. So if this works, 7 and 4 are the quotient and reminder. They gotta be unique. It's not possible I get 7, 4 and he gets some other numbers. There's only one quotient and one reminder. With a condition, the reminder have to be in this set. So I've got this 4, and what am I gonna notice? 4 is already in the list somewhere, right? If I am to keep going, so I started with 2, I got then 4, then I got 5 by repeated squaring, right? 5, 3, 9, 4. What happens if I square this one again? What do you think is gonna happen?
Get 5.
I'm gonna get a 5 and then squaring that again, 3 and that again, 9 and 4, and I can do very quickly powers of 2 up to like 256, 1024, because this is just a cycle that keeps repeating here, right? Because if I add a 4, the same thing can happen. When I square it, it's gonna be 4 squared, 5, 5 squared, so on and so forth. Yes?
Sorry, when you said that you did a quick check using one of those rules, I missed which one you pointed at.
This. This main equation of, this is called the integer division. So I just figured out what quotient I need, 7, to make this equation work. Right? 77 plus 4 is 81. Once I see that, I know for sure 7 is the quotient, 4 is the remainder. The quotient is not important to me right here. I don't need the quotient 7. Maybe I'll need it later on, but here is just a check that 4 is indeed the remainder. Back to my original problem, I think everybody can see how easy it is to do this now. I have a bunch of powers of 2 exponents for 13. I only need to compute, I go back here and I say, okay, 13 to the 14, that's what I started, is 13 to the 8, 13 to the 4, modulo 11. So 13 to the 8, how much was that? 3. All right. 13 to the 4, where is it? Here. 5. And 13 to the 2, 4. Let's draw some nice arrows for people who are watching this video to know 5 is from here, 4 is from here, and the 3 from here. Now that's very easy to do. So if I'm to do that, I can even break that into parts. If I'm too lazy to compute the product and then take modulo 11, I can say I want to do 15. That's modulo 11. I can do 15 mod 11 times 4 mod 11. Now 15 mod 11 is 4. So that's 4 times 4 mod 11. How much is that? 5. So when somebody says repeated squaring, it's not necessarily for the modulo stuff. We've seen it with matrices, we've seen it with other numbers. It's just a fast way to do multiplications. Multiplications are typically expensive for any CPU. Even the most modern CPUs do faster, much faster additions than multiplications. So when people calculate how computationally expensive it is to do matrix operations, big matrices, they don't count the additions usually. When people do fast matrix algorithms, like in MATLAB, they don't worry about the additions. Additions are considered like zero expense. They worry about multiplication, inverses, logarithms, things like that. The additions themselves are considered super fast. It takes hundreds of additions to take the clock time of one multiplication. So in here, without looking at the additions, I'm saving on multiplications. Instead of doing 14 multiplications, 13 times 13 times 13 times 13, 14 times, I only did 1, 2, 3, because each squaring is effectively a multiplication. It's multiplying with itself. And then I had to do 2 more multiplications to get the 14 power as a product. This trick works in a lot of cases, not just in modulo arithmetic. So at mechanics, the last thing we want to recap, I wanna show you for visual purposes some modulo n equal 3, some addition and multiplication tables. So Z3 is of course 0, 1, and 2. So I have here 0, 1, 2, 0, 1, 2. This is just in case this is still not clear. And I'm doing the addition. So this is the addition. If I add 0 to 0, I get 0, 0 to 1, 1, 0 to 2, 2. Of course, adding 0 skips whatever you have. Same thing here, 1, 2. What if I add 1 with 1? 2. What if I add 1 with 2? What am I getting here? 0. This is all addition mod 3. And if I add 2 to 1, I get 0. And if I add 2 to 2, I get what? 1. You see how modulo, I'm always in that space 0, 1, 2. I don't get out of it. What happens if I do the multiplication? It's 0, 1, 2, 0, 1, 2. Let's try to do the multiplication. So this is multiplication modulo 3. 0 multiplied with anything will be 0. Multiply with anything will be 0. 1 multiplied with everything will be that thing. 1 times 1 is 1. 1 times 2 is 2. 2 multiplies with 1 is 2. 2 multiplies with 2 is? That's the multiplication. Let's do here n equal 4. Z4 here is 0, 1, 2, 3. That's one more reminder. So I'm going to build these tables. 0, 1, 2, 3. 0, 1, 2, 3. Okay, let's do the additions. Addition, this is modulo 4. 0 doesn't change anything when I add 0. Same thing in here. 1, 2, 3. What happens if I add 1 to 1, I get 2. 1 to 2, I get 3. 1 to 3, I get 4, which is 0. 2 to 0, 2. 2 to 1, 3. 2 to 2, 0. And 2 plus 3 equal 1 in modulo 4. 3 plus 0 is 3. 3 plus 1 is 0. 3 plus 2 is 1. And 3 plus 3 is. And the multiplication? 0, 1, 2, 3, 0, 1, 2, 3. 0, when I multiply with anything, I get 0, 0, 0, 0. When I multiply 0 with everything, I get 0, 0, 0. Now 1 multiply with everything is that line, so this will be 1, 2, 3. Same here. 1 multiply with everything will be 1, 2, 3. Now 2 multiplied times 1 is 2. 2 multiplied times 2 is 4. That's a 0. 2 multiplied times 3 is 6. That's a 2. 3 multiplied times 1, 3 times 2, 3 times 2, 6. That is 2. 3 times 3 is 9. 9 is 1. So I put those things here, and I'm asking you to write them down so that visually you have the mechanics. I know you understand conceptually how it works, but you need to visualize this mechanically, you know. And there is a lot of observations we can do here. This is increasing by 1 on that circle that we drew last time. 0, 1, 2, 3, 1, 2, 3, 0, 2, 3, 0, 1. That's all the ticks on 0 was here, right? 1, 2, 3. So if you see every row in the addition table is just this whole circle shifted by 1. That's not the case here, right? Look at this guy. 2 becomes, this row is 0, 2, 0, 2. Clearly this doesn't look like that circle shifted. So multiplication is a lot more complicated modulo than the addition. In fact, one thing that I want to get to today or next time is in addition, I can always get a 0, right? Every reminder has something I can add to it to get a 0. So I want to express that fact in addition. I want to say for addition, modulo n, I want to say every integer x, there is an integer y in Zn, one canonical reminder, such that x plus y equals 0 modulo n. Everybody has something I can add to it to get to 0. The reason is, wherever I'm on the circle, there is an amount I can add to get to 0. Right? This is how many ticks I need to add. Anybody knows what that integer is? What? So take, for example, in here, example, take n equal 11 and take x equal 72. Just picking a random number. What is the integer y? I'm asking for a canonical reminder, not just any integer. What's the reminder I need to add to 72 to get to 0 modulo 11? So I need x plus y equals 0 modulo 11, but x is already 72. 72 plus what gives me 0? 0 is really a multiple of 11. Right? That's what 0 means. Every time you see 0 modulo arithmetic, it's a multiple of n, which in my case it's 11 here. So how much do I need to add to 72 to get to a multiple of 11? How much? 5. So that y is 5 in this case. Again, on a circle, let's draw the circle for 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where is 72 on the circle? 72 modulo 11 is where? 6. It's here, right? That is the same as 672. So now, how much do I need to add to get to 0? How many ticks? 1, 2, 3, 4, 5 ticks. That's why I got y equals 5. And this number, the number of ticks I need to add to get to 0, it's always less than the ticks, the whole circles, right? That's why this y, it's always in Z11. It's one of the canonical reminders. In other words, it's between 0 and 10. Yes?
Is this way of representing things with the circle something we need to learn how to do and use?
I use this for intuition purposes only. I think it's very useful if you don't have a handle of numbers and reminders to see that way. We're not going to ask formally to draw the circle. I don't think so. So I don't think you are required to see things that way with a circle. Some people find it easier. If you don't like the circle, if you understand it easier algebraically, that's fine. All right. Can I say the same about multiplication? The same exact statement. How would this statement read for multiplication? If I want to say the same. I'm going to say whatever x in Z, there exists a y canonical reminder, right? Such that when you multiply x times y modulo n, you get not 0, right? Because 0 is the one for addition. What's the neutral element of multiplication? 1. First of all, this cannot possibly work for 0, right? If x is 0, or any 0 modulo n, 0 times something will always be 0. So to make this possible at all, I need to say x is not 0 modulo n. In other words, x is not what? A multiple. 0 means multiple of that number. When somebody says 0 modulo 75, that's a multiple of 75. Any multiple of 75. So now that I added this condition, which seems necessary, I can't get it to work with x equals 0. Is this true? For every x modulo n, there is a y that x times y gives me 1. Some people bang their heads left to right. I take it that's a no. Is there an example for this thing? So what n? The answer is no. Counter example. I use here 11. What n and x do I need to use to have a counterexample? How about 26 and x equal 2? Is that a good counterexample? In other words, what I'm saying is, for any y anybody picks in Zn, you can have 2 times y equal 1 modulo 26. So as a counterexample, take n26, x equal 2. 2 cannot be multiplied to anything to get to 1 modulo 26. How many people follow me here? Hands up. Now, sometimes that is true, right? I mean, suppose I take n equal 26 and x equal 5. Is there a y? I need to multiply 5 times y to get 1 modulo 26. Is that possible? Is there such a reminder? Y has to be a reminder, one of the reminders. Is there a reminder that I can put in here to get what is it? This is not a philosophical question. If you say yes, you have to give me the reminder. Anyway, we get to talk a little. You guys can think about that. I'll get to it in a second. Now I'm done with the mechanics. That's the part that everybody should know, how to operate modulo n. Additions, multiplications, raising to the power, things like that. So what I want to do now is to move a little bit into theory, actual number theory. This is just what operations we need for everybody to be on the same page. If anybody knows this y, please give it to me. Yes? 21. Because 5 times 21 is how much? 105, which is 105 modulo 26. 105 is 26 times. What's the quotient? 4. That's how much is this? 104, right? Plus 1. So this gotta be 1 modulo 26. Again, I do that basic brute verification. I'm not sure it's 1, so I do the integer division to see it clearly on paper. What's the quotient? What's the remainder? So you can see how for addition, I can always get to 0. And if I can get to 0, means I can get anywhere, right? Once I got to 0 by addition, I can add something to get to any remainder I want on the circle. But with the multiplication, it's not so clear. Since we answered this question, let's follow this thought a little bit for this circle that is the 26 circle. So this is 0. I'm only going to put the even one. 2, 4, 6, 8, 10, 12, 14, what is it, 16, 18, 20, 22, 24, right? I have nothing here. Because 26 is in here. This is n equal 26, and I skip some of them. Of course, they are in here. That's 3, that's 5, so on and so forth. The reason I can't get this to work for 2 is that if I start at 2 and I multiply with anything, y, I multiply y equal 1, y equal 2, y equal 3. If I multiply with 1, stays at 2. If I multiply with 2, I get the 4. If I multiply with 3, I get the 6. If I multiply with 7, I get the 14. And if I multiply with 13, I get back at here, right? This is times 13. This is times 7. My point is, when you multiply 2 with all possible reminders, you only get the even ticks here. 2, 4, 6, no matter what you choose to multiply with, you can never get the odd ticks. And we can see this algebraically. 2 times anything will have to be n, that is 26, times a quotient plus a reminder. Why is it that this reminder that I'm obtaining, it's always the even ones? Why is that? Yes?
Because since 26 is even, it's gonna, like 26 times q is going to be even, and you have to, even plus even equals even.
So I think what she's saying is you can look at r as being 2y minus 26q, right? And she's saying this is an even number. Now this is not a modulo operation. This is an actual integer. I don't want to do it modulo here. I'm actually writing the integer division out, so I don't have any modulo. Those are integer values. So this is even, and the operation with even numbers here, this implies r must be even. Now even if I take modulo 26, r modulo 26, that's still going to be even. Right? So the point is, you cannot get the odd reminders no matter what. Now the one I like happened to be an odd reminder, so I can't get this one no matter what I multiply. We'll get to this a little further down the line, today or Friday, to why, more generally how this happened. But it's important to know that with additions, I can get to 0 or anywhere I want. With multiplications, of course, if I get to 1, from there I can get to what I want. If I can multiply to get to 1, and then I say I want to get to 7, I just multiply the 1 with 7, and I got to 7. But in some cases, I can't get to 1, which means I can't get to quite a few of these reminders by multiplication. So why is this so important? The basic ciphers that we've seen was the Caesar cipher. Caesar cipher was saying, take the message, let's call it x, that's an integer. And the encryption was, anybody remembers? What did we do to encrypt the message? To write the letter in a way that no one else can read it. So added 3, right? We say x plus 3, and then we took modulo. Because we went, when it was over the end, we went back from the beginning. That's like a modulo operation on the cycle. It was modulo 26, right? So let's call that y. Y is x plus 3 modulo 26. That is the cipher. That's the encrypted stuff. Of course, for this stuff to be useful, I need to be able to decrypt it. On the other hand, somebody gets the letter and is the person intended to read it, has to be able to decrypt the message. So how is the decryption working? If I see this letter written, every character moved by 3 positions, what do I have to do to get back the original content? Do the opposite operation, which is? So what I need to do is to get back x, I get a y minus 3 modulo 26. Now, in terms of what I just said, add something. If I don't want to subtract 3, I could say y plus how much? Get the same exact effect. On a circle, if I go 3 ticks to the left, is the same as going how many ticks to the right? 23. I could do that instead. Is that guaranteed to work? If I move 3 ticks to the right, can I move back 3 ticks to the left? Or add another 23 to the right? Hands up, who's with me? That's guaranteed to work, right? But people have figured out, hey, that's too easy to decrypt. If somebody intercepts 2 or 3 or 5 letters, they're going to know what we're doing. So they came up with a slightly more interesting idea. We call that the linear cipher. Guess what it is? I get a message, X, I encrypt. Let's say in Z10, to not complicate ourselves, we'll have to deal later on at some point with how do we get messages in Z10. But let's say we start with Z10. So the encryption function is just a little more complicated. It says not just add 3, but multiply with something, like X plus 5 times 5 plus 3 modulo 26. Everybody sees the difference here? Instead of just shifting the thing by 3, it multiplies by 5 and then shifts by 3. A linear operation. This is the cipher. So that's encrypted. Presumably, this is harder to intercept and read, right? Because it's not just plus minus 3. This is a times 5 in there that makes things complicated. What do I need to do for decryption here? Yes.
Subtract 3 from y and then multiply.
So subtract 3 first of all, because it's the inverse operation. This had this 3, I'm going to take 3 out. And then
Multiply by inverse of 5.
multiply by this magic something, inverse of 5. Let's say that's the z. That's the same thing I've asked you guys in here. Can you multiply with something to get a 1? And then I need this to be back x. So who's this z? You say who's the z? Is the inverse of
5.
5. So we call that 5 at minus 1 modulo 26. That is the stuff that we ask here. It has the, what do we mean by 5 at minus 1? This is just a notation. We mean the number that multiply with 5 gives me 1. It's the same thing. So z, it's called inverse of 5 modulo 26. Is the number that I can multiply 5 with to give me 1. And you can see why that works in here. Right? Let's parse this equation again. How much is y minus 3 times the inverse of 5? Y was, by encryption, x plus 5, x times 5 plus 3. Now it's that minus 3 times the inverse of 5, 5 at minus 1. So that is now x times 5 at minus 1 modulo 26. 5 and 5 at minus 1, by definition, this inverse I'm looking for is the one that if I multiply 5 with, I get 1. Therefore, this is x times 1 modulo 26, which is back x. Which is the purpose of decryption. To get what I had initially, decrypt it back, read the letter. Caesar sent to me, right? This is not a small issue. Like, we of course look at it and we laugh, hey, look at these guys, what they did before. But you know, entire empires, at some point or another, dependent on who reads what. There's so countless issues in history when, because I knew this and I didn't know that, something happened, caused a war, and somebody, the entire civilization disappeared. So it's not a small thing. Very recently in World War II, United States completely sink the Japanese fleet in the Pacific because they knew where those carriers are. Now we're laughing and look, how can you miss a carrier? Like now everybody can see where the carriers are, right? Even non-military people, because they're so big. Well, in 1942, people couldn't see where the carriers are. It was not that easy. So United States fleet was looking for the Japanese fleet, and the Japanese fleet was looking for United States fleet. They were roughly equal powerful. In fact, the Japanese have slightly better planes, and the United States has slightly better aircraft carriers. Guess what? The United States sink 3 carriers before the other guys even knew what happened, because they knew where they were. They were tracking them for days. That's a battle of Midway, I think it's called, in the World War II history. It's all about information. Now, after that, this has important consequences because the Japanese couldn't rebuild their fleet, therefore they lost the whole war. So encryption and decryption matters a lot. Not to say today everything is encrypted from basic personal bank accounts encrypted. But even this, it's easier to break. It looks a little harder than the first one, but it's not hard to break. If you see a lot of pairs X and Y, it's hard. Before, when we break a Caesar cipher, we don't need X. We just need Y with some trials, how many ticks I have to go back to make sense. And I get the plus of -3. In here, I'm going to need a bunch of X and Y pairs, like the original letter and the encrypted letter. If I get a bunch of X and Y's, I can figure out those coefficients, 5 and 3. And then once I know the coefficients, I can decrypt anything. There are much more performance systems based on number theory. In fact, they are using number theory in practice a lot. It's called RSA, the crypto system that most banks and securities softwares are using. It's much more complicated than this. If we have time, we'll see how that works Friday without proofs. Okay, so let's recap. We have the encryption message, we have this linear cipher, but what's the problem with these linear ciphers at decryption? If I pick the 5 without being careful, I can't decrypt it. So see what happened here? If I pick the 5, I know it has an inverse. So the inverse, I need this Z. I know Z is 21, or 5 at -1. We just done that in here. If you want which number multiplied by 5 gives you 1, the inverse, this Z, I know there is 1, there is 5 at -1. But what if instead of 5 I choose 2? So instead of this 5 I say X times 2 plus 3. Would the encryption work? Can I take a message multiplied by 2 and add 3? Of course it works. I get a number, right? What doesn't work? I can't decrypt it back. What's the reason? 2 has no inverse. I can't get this Z here to allow me to do the decryption. We just did it here. 2 has no inverse, so I can't decrypt this cipher back. Doesn't decrypt. Because 2 doesn't have an inverse. Modulo 26. Okay, once again, who's with me here? I can get these linear ciphers to work, multiply with a constant and add something, with the condition that what I multiply with, the 5, has to have a number that allows me to inverse it, aka multiply with 5 to get 1. So with that as our motivation base here, there are a bunch of results for number theories that you're going to get from these notes. And I want to start with a summary of what we want to do. And then let's see how far we can go. So one is factorization. We already talked about this. Any number n is some p1 at e1 times p2, factorization into primes. e2, pk at ek. Well, pi's are primes, ei are the exponents, because they got to be at least 1. And this is unique. A number can only decompose into primes one way. For example, let me write this here. 12 is 2 to the 2 times 3. So the prime numbers are 2 and 3, that's the exponent. That you can say 3 at 1. 48 is 2 to the 4 times 3 to the 1. 36 is 2 to the 2 times 3 to the 2. 1, 4, 5, 2 is 2 times 2, 2 at 2 times 3 times 1 times 11 squared. So these factorizations, which always exist, and they're always unique, have primes at the base and some exponentials powers at least one. I'm sure you've seen this before. It's important to know this factorization is unique. And if you study mathematics, not computer science, there's a proof why this factorization is unique, why you can have two different factorizations. Apart from rearranging the factor order, this got to be a one thing on. So that's one thing. The first theorem or lemma that we need here, the first result, is that if A is the same as B mod n, that's equivalent to say n divides n minus b. So two numbers have the same remainder. If and only if n divides the difference. So for example, let's see here. (36) modulo 11 is the same as, let's say, 58. Right, because 36 mod 11 is how much? 3, which is the same as 58 mod 11. Those two have the same tick on the 11th circle. The theorem says that's the same as saying 11 divides 58 minus 36. The difference have to be a multiple of 11. Is that true? Multiple of 11. So you know when two numbers have the same remainder, if the difference is a multiple of 11. It works backwards too. If the difference is a multiple of 11, they have the same remainder. We can try a little proof here. If A is n times q1 plus r, and B is n times q2 plus r, the quotients can be different. But the reminders are the same. That's what the theorem is saying. This A equal B mod 11 is a statement about the reminders, not the quotients. Well, how do I get to say n divides? How much is n minus b? R goes away with r, and I get n times q1 minus q2, right? Which means n divides a minus b, because a minus b is n times an integer. The full proof is in the notes. It's a very easy thing. And it's very important in many proofs, you have to start there. To control the fact that two things have the same remainder, you have to play with the difference. That's the internal guts of the proof. Result number 3. I didn't say what a prime is, but everybody know what primes are, right? What is a prime number?
Only one. It's only divisible by 1 in itself.
Right. So the primes are where? What are the primes?
2, 3, 5, 7, 11, 13, 17, 19, 21, no, 23, 29, 31, 37.
Primes are the one divisible just by 1 and themselves. Now here's another result that we need. If a P prime, P divides a product A times B, implies P divides A or P divides B. A prime, when it divides a product, has to divide one of the factors. That is not true if P is not a prime. So very important, not true if P is not prime. For example, if P would be 10, 10 divides the product 4 times 25, right? Is that true? But 10 does not divide 4, and 10 not divides 25. So this is true when P is prime. A prime divides a product only if it divides one of the factors, but it's not true if P is not prime. Now, this is easy to see. We don't really need a proof, because what's going to happen in AB factorization to be divided by a P prime, that P has to be one of these. The only, in the product, if I do A times B, I'm going to get the product of factors. P has to be one of those primes. But the only way they get primes is they get it from A or to B. So for a P prime to appear in the product, has to be coming either from A or from B. In each case, A or B is divisible by P. Again, the detailed proof is in the notes.
It could be divisible by both, right?
Yes, it could divide both A and B. Or doesn't mean it's not an exclusive or, it could be both. So far so good, that's easy. Here's another one that we need to do. Let's move in here. 4. The GCD stands for what? Greatest common divisor. LCM, least common multiple. Maybe you remember from, what do I have here, 1452? You remember from way back that the way you defined this, maybe in high school or before, it literally was the greatest number that does something, right? It's a common divisor. Everybody remembers the definition from high school? It's the biggest number. I want you to forget that definition. Very dangerous, all right? I'm not saying it's incorrect, it's correct, but that is completely not operational. The biggest number that divides 36 and 48. I have to try out numbers to see what's the GCD, right? How do I know which one's the biggest? I want a different definition, one that actually I can operate with. So that is correct. It is the biggest, but we're going to get that as a theorem, not as a definition. What we want to say here for the greatest GCD is the common primes at lowest exponents. So from now on, GCD has nothing to do with the greatest or the lowest. What it has to do is, I look at 36 and 48, GCD 36 and 48, and I'm looking at what are the common primes in there. Do I have 2's common? What's the smallest number of 2's? Some that's common to both of them. I have 4 in here and 2 in here. So the lowest exponent is 2. And I have 3's, 3 at 1 and 3 at 2, so that will be times 3 at 1. That's the GCD. I take the common primes at the smaller exponent. That's how I make the GCD. And how about the LCM? All primes at highest exponents. So LCM of 36 and 48, if I do, how many 2's, what's the biggest number of 2's in there? 4 times 3 to the 2, right? Okay. How about if I get, here's another example, A918 is 2 times 7 to the 3 times 13, decomposition into primes, while 9800 is 2 to the 3rd times 5 squared times 7 squared. What is the GCD of those two guys? Forget about the greatest anything. Again, I want you to forget that definition because it's completely unusable to find the GCD. You're not going to try various values in here to see what's the biggest that divides both of them. That will take forever. Decompose it into primes. Say, what are the common primes? Is 2 common? At what power? 1. 3 is 3. I don't have 3s. Is 5 common? No. It's 7 common? At what power? That's it. How about the LCM? I take all primes, not just the common ones. So at the biggest power, 2 goes at what power? 3. 5 goes at what power? 2. 7 goes at what power? 3. Am I done? I need a 13 at power 1. Right? So as a theorem, indeed, this value is the greatest number that divides the two, and this value is the lowest that multiplies. It's a multiple of both, so we can prove that. In fact, it's proven in the notes. But that's not how we want to operate with GCD and LCM. We want to take the primes. For GCD, the commons one are the lowest exponents. For LCM, all of them are the highest exponent. Let me see if I have another example. Let's do one more. 60 is 2 times 2 squared times 3 times 5, while 50 is 2 times 5 squared. So what's the GCD? 2 times 3? No, 5. And then the LCM? 2 squared times 3, 5 squared. Here's result number 5 that you can prove as an exercise. The product of two values is the product between their GCD and the LCM. So we can check it right here. If I multiply 60 times 50, I can multiply the primes. I get 2 at what power? If I multiply 2 2's with 1 2, I get 3. 3 2's. 3. It's 1 3. And how many 5's? 3. And you can see that this is exactly if I multiply those two together. So this is exercise. Try to do it by yourself. The proof is in the notes. That's very useful to compute one of those things. If you know the product, it's usually an easy thing. And if you know the GCD, you immediately can get the LCM. And if you know the LCM, you immediately can get the GCD. So this could be a useful thing. When you know the GCD, how do you compute the LCM? Okay? Now, how do we find the GCD other than prime decomposition? While this is all good in theory, all cryptographic systems rely on the fact that what makes security in all cryptographic systems work? Why is it difficult to break in? Anybody knows? Yes?
Just these really big prime numbers.
Factorization is hard. If I give you a large number with many digits and I say decompose it into primes, that's a hard problem. Nobody knows how to do that efficiently for big numbers. If somebody figures that out, a lot of the crypto systems in the world go down. All cryptography today relies on the fact that numbers cannot be easily factorized into primes. So, of course, this is all very nice, right? Assuming I have the prime factorization. Because GCD relies to say common primes, right, between the factors. If I don't have the prime factors, then what? So, the Euclid algorithm for finding GCD without factorization. Because with factorization, it's easy. That's result number 6. Euclid actually didn't do it efficiently, so he did it, it worked, but then some mathematician later on look at it and say, wait a minute, this can be done much faster than this. So what Euclid says, you want the GCD of A and B? Well, you can, let's assume A is bigger than B here. That's the same as the GCD between A minus B and B. So his idea was to make a problem a little smaller and then keep going, right? That's the same as the GCD, maybe A minus 2B and B, and then later on subtract it backwards until we get to GCD of small values. The idea is that subtract the smallest from the biggest. So how that work if I do GCD of 22 and 6? Euclid will do what? Subtract the small from the big, I get what? 22 minus 6 and 6, right? That is, how much is 22 minus 6? 16 and 6. If I keep subtracting the smallest from the biggest, I get 10 and 6, right? Which if I subtract again, I get 4 and 6. Now, when I subtract, it's backwards, because 4 is the smaller one I subtract from the 6. So I get GCD of 4 and 2. And if I subtract again, the smallest stays always. The bigger one gets to be big minus small. I get what? And that's easy, right? How much is the GCD of 2 and 2? It's easy to see that the GCD between a number itself is that number. So this is saying that the GCD between a bigger number and a smaller number is the same as the GCD of the smaller and the bigger minus smaller. Now, there's two issues here. One is why is it true? Can we just count on this fact? Why is this always true? In other words, instead of doing the GCD between two big values, I can get it down, 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 down. I still don't know what the GCD is, but the problem gets smaller and smaller and smaller, and at some point I know what the GCD is because the numbers are very small or identical or something I can do. But why can I say doing this operation does not change the GCD value? There's got to be a mathematical thing behind the scenes. That's the Euclid contribution that he said, you know, you can get the problem smaller, it preserves the GCD, so you just find the GCD at the end, that's the one you need. Secondly is, how do we make this faster? Later on, people have thought, wait a minute, that's going to take a lot of subtractions here to get to the answer. Can we do it faster? So those are the two things that we need to go by. Before I do, I want to show you another example. How about between, what do I have here? 51 and 9. You guys can tell me quickly what are the steps. GCD and 9 and GCD of 9 again and GCD of 9 again and GCD of 9 and GCD of 9 and 6. Now they have swapped. The small is not 9 anymore. So this is GCD of 6 and 3. Swap again, GCD of 3 and, which is? Hands up, who's with me on this? Easy to do subtractions, right? Yes. This?
Yeah.
Where do I get a 42?
And once you switch it.
Oh, because I said here between bigger and smaller is smaller and bigger minus smaller. GCD is doesn't matter how you put it, 42 and 9, 9 and 42. You like it better, 42 and 9?
No, you don't have to change.
The point is subtract the small from the big.
Okay.
So at some point, 9 is not the smallest anymore, right? I get 9 and 6. And here I swap. I take the 6 out of 9, so 6 stays, and I get the difference. Okay? Now, why is this correct? What's the mathematical behind the scene here that makes this a correct statement? So what we want to prove, the theorem, is that the GCD between A and B is the same as the GCD between A minus B and B. That's the theorem that says if you take the smallest, let's assume A is bigger than B. If you take the smallest out of the biggest and you keep the small and the difference, that's the same GCD. That's how we want to prove what we want to prove. So how do we do this? Yes.
Theorem 2 on that board might help.
Which one?
Theorem 2.
This one? It says they have the same reminder if the difference is a multiple of n. So we don't have an n here, right?
Oh, yeah, we divide it.
Right, so we have to work out a little bit how this happens. What I think it's useful to start here, in many number theory problems, the useful place to start is to say, I'm going to do the integer division. The integer division is A is B times Q plus R. And R has to be in ZB, which is 0, 1, up to B minus 1. When you do an integer division, you get a quotient. Quotient can be any integer, but R has to be a canonical remainder by division of B, which is from 0 to B minus 1. So now let's say the GCD between A and B is some D. Right? How do we, that is the GCD between A and B, so that is the GCD between B and BQ plus R. This is just A here. I rewrote A as that. What we want is to say D is the GCD between B and A minus B. That's equivalent of saying D is the GCD between B. How much is A minus B? It's B times Q minus 1 plus R. This in here is A minus B. Okay? If I take A minus B, I get BQ plus R minus B, that's BQ minus 1 times R. So this is a proof that I would like you to play a little bit with it and then to recap it, say, next time. Yes? Question?
What do you put after B on the last one? Is it B times Q minus 1?
Yeah. Is that clear where it's coming from? So how much is A minus B? Is BQ plus R, that's A, minus B. So I do a B common factor, Q minus 1 plus R. The reason I want to show those two have the same GCD, AB and A minus B, what I want to prove is that anything that divides both A and B will divide N minus B. So my plan for this proof, this is just rewriting what I want. Here's the proof idea. Any D that divides A and divides B has to divide, I think somebody already mentioned that, A minus B. That I know from some property in there. And the GCD divides A, right? This is the GCD. So if GCD divides A and B, GCD will divide the difference. That's one step. I want it also the other way. if some number g divides a minus b and divides b, then g divides a minus b plus b. That means g divides a. So anything, g is the GCD of a minus b and b. This is easy, just you have to write your mind correctly about it. The GCD of a and b has to divide a and has to divide b by definition, is the GCD. So it divides both of them. If it divides both of them, it has to divide the difference. The other GCD that I need, b and a minus b, divides a minus b and divides b. By definition, is the GCD between them two, so it's a common divisor, so it has to divide both. If it divides both, it has to divide the sum. My plan here is to show that those two are the same, d and g. D is the common divisor between a and b, greatest common divisor, and g is the greatest common divisor between a minus b and b. So how do I show that they are the same? One divides a and b, therefore the difference. The other divides the difference and b, therefore a. So overall, they have the same property. D divides a, b, and the difference. G divides a and b and the difference. Why are they equal? Somehow, what I want here is a series of implications that leads to d equal g, right? That the greatest common divisors of this and that are the same. How do I move along this path? This is an easy proof. When you get fluent into who divides what and for what reason, this is not complicated. You don't need almost any line in here. Just wrap your mind correctly about it. And this is something that I don't want to say in class, because if I say in class, nobody's ever going to think about this. People go home, turkey month, forget it. Right? I want you to think about and come up with some ideas. What is necessary here to get to d equals g? Again, it's not hard. Keep in mind that the greatest is the one that is the greater. You can't get the greater than this. So intermediary, at some point in here, I want to say d divides g, and on the other hand, g divides d. Divides each other. So if they divide each other, they got to be equal, right? Because the only two numbers that x divides y and y divides x, the only way that to happen is if they're equal. But how do I get to here? This is your exercise for next time, and we'll do it in class. But please, give it a thought. How do I get that those two GCDs are the same? In case you get stuck today and very curious, the proof is in the notes. Now, assuming we get that done, everybody can see the mechanic. Subtract the smallest from the highest, keep going until you get two equal numbers. That's your GCD. Somebody figured out, hey, I can do this much faster. I don't have to do all these fractions. Instead, I'm going to do something else. I'm going to compress a bunch of subtractions into one step. So for example, I'm going to look at all this. What happened here? What was the quantity subtracted? 9. How about in here? This is a minus 9, right? What happened in here? Minus 9. What happened here? Minus 9. Minus 9. Minus 9. All these minus 9s, I could have done it in one step. Here's how. Instead of do the subtraction, I say, I start with A, B. B is A and B, 51 and 9, right? That's a B. And instead of moving to 51 and 51 minus 9, like I did in here, I'm going to do the integer division first. What do I get? 51, 9. What's the quotient? What's the remainder? The next step in Euclid algorithm, the next A is the previous B. Previous B. Who is that? 9. And the next B is the previous R. Who's that? So on 9 and 6, where did I jump in this whole chain here? From 51, 9, this is where I started. Where did I move on? If I just do integer division and say my next A is B and my next B is R, where in this chain I jumped? Right here, right? Isn't that magic? It's not magic. What happened here? How many steps I did before? 1, 2, 3, 4, 5. What was each one of these steps? Subtracting a 9. And why did it happen 5 times? Because there's 5 9s in there. So if the quotient says it's 5 9s, what really happened here, I took 1 9 at a time. In here, what happened? I took 5 9s in one shot. So I got directly to 9 and 6. So you see how it's the same pipeline, but just moving all the 9s that are subtracted, 1, 2, 3, 4, 5, cut them down in one step. So if I do again the quotient, the remainder, what do I get?
1, 3.
So my next Euclid line will be previous B, 6, previous R, quotient,
2.
2, remainder, 0. Now, if you see remainder 0, that's a stop. Where is the GCD?
It's B.
This B. Last B is the GCD. Last B, when you see remainder 0, that is. Let's do it for the 22 and 6. This other example here, the first one. A, B, Q, R, 22. Write it a little bit further. A, B, Q, R, 22, 6. Quotient.
3.
Reminder. So when I jump over, this is the next, the previous B, and this is the previous R. So what's the previous B? 6, previous R, quotient, reminder, 4, 2, quotient, 0. That's a stop. So this is the GCD. GCD plus B. Hey.
I just have the midterm.
Yes, the midterms, right. Give me, can you stay for a little bit? Yeah, give me 10 minutes because I'm afraid once we give the midterms out, I lose everyone's attention. I can do whatever in front, it won't matter. So give me 10 minutes and then we distribute the midterms. All right. Again, what happened in the first step there? How many 6s did I have to subtract if I followed the original Euclid? 3 6s, right? Did that happen? Did I subtract 3 6s? This is a minus 6, minus 6, minus 6, right? Instead of that, I could just do it on step and then end up with 6 and 4, right? So this is just saying, instead of subtracting all these b's one after the other, you can compute in advance how many b's you want to subtract and directly move into B and R, which is the next step. This is a logarithmic compared to a linear optimization, right? Instead of doing in linear time, because for each B you go one step, I can do it logarithmically because I do all the B's at once. And there is other proofs that you can do regarding the speed of this modern Euclid. It's extremely fast. It's actually being used today even with large numbers because it's logarithmic in the size of the numbers. It's the number of bits. Even if I have 3,000, the number there is in cryptography are 3,000 digits long. So I can't really deal with the numbers themselves, but if it's logarithmic, it's 3,000 digits. I need to do 3,000 operations. So I get that. That is the Euclid. And a lot of the problems, quizzes, exams, recitations will be about GCDs and Euclid. So you need to be very fluent into that. Now, the last thing I want to say, these 10 minutes, that I need to go to the, that's going to spill into Friday. Go back to this inverse idea. Where there is an inverse and where there's not. We already said, here's a multiplicative inverse. Modulo n. So we say if A is a Z, there exists A at -1. That's Z in Zn, canonical reminder. We call it multiplicative inverse. If A times A at -1 is 1 modulo n. So for example, the example we had in there was if 5 has multiplicative inverse, modulo, what modulo was here, 26? 5 at -1, we said is 21. 5 at -1, just written like that, it means there is an inverse without saying which one is it. If you want to say which one is it, you have to point to the actual reminder that is 21. And we said before, it doesn't always exist. Does not always exist. So our concern is when there is one and when it's not. And if there is one, how do we find it? For decrypting linear ciphers, we need our hands on that inverse. Whoever we multiply with, that was the 5, we need to know what to multiply with backwards to get back to the original number. That would be the 21 because it's the 5 inverse. But because inverse is not always there, we need to know when it's there and how do we find it. So the multiplicative inverse questions are when there is A at -1 modulo n. What does it make inverse possible? And 2, how to find it. This is required for everybody, including the regular section. You have to know where it is, but we're not requiring for exercises, quizzes, homeworks, and exams how to find it. Of course, we in here, we're going to find it in 3 ways. But that's not required for your exam. You're not going to get an exam question that says, find the inverse. Now, so you can ask, okay, if we know how to find it, but the regular section doesn't know how to find it, how do they find it? Well, if I don't show you how to find it, how would you find it? Trial and error, right? Try a bunch of things. How did you get this 21? Did you trial and error?
Well, I just thought of multiples. It was really by chance.
Right. So that's how you do it. If you don't know mechanism to find it, you guess the inverse. You should know whether there is one or not, because if you don't know that and you try, you can try a long time and never find anything. So you should know when there is one. And if there is one, if you don't want to learn the procedures, like I said, they're optional. You just guess it until you find the one. Now, for the other students, we're going to show 2 ways of finding this inverse. So, one way is to modify Euclid a little bit. There is an extended Euclid theorem. So that's the Euclid here, the theorem from Euclid. The extended Euclid theorem, which we're going to do without proof. But it's fundamental for number theory, cryptography, and some algebra. It's a fundamental equation. It says not just there is a GCD, It says you want the GCD between A and B. That's A times X or H. How do we call it here? X plus B times Y. So this one says you can find two coefficients, X and Y. Those are integers. And you can get the GCD as a linear combination between A and B. Finding X and Y, it's a fundamental mathematical operation that characterizes the integer set. So if you do any mathematics, especially cryptography, you're going to have to handle this equation very well. It used to be required for everybody in this class as part of the reshuffle. Now it's not. It's not required for you either. But I'm saying it's a fundamental thing to do anything in number theory. If you knew how to find X and Y, the inverse is very easy, right? Think about it. I want 5 times the inverse to be 1 modulo 26. What happens if I think of the GCD between 5 and 26? How much is the GCD between 5 and 26? Greatest common divisor. 1. Well, that theorem there is going to tell me that's 5 times X plus 26 times Y, right? That's what the theorem is saying. The GCD can be obtained with some two coefficients X and Y. So where is the inverse of 5 modulo 26 in here? Do I have the inverse of 5? If I put my hands on this X and Y, can you tell me the inverse of 5? Again, I don't know how to find X and Y, but the theorem says there is a way to find them. If I have this X and Y to get me the GCD, where is the inverse of 5 modulo 26 in here? Because it's right here written on the board already. Isn't this X the inverse of 5? That times 5, modulo 26, this is 0, right? It's a multiple of 26. So X gotta be the inverse of 5. So that theorem, that's called the Bezout equation. It immediately finds the inverse if the GCD is 1. Okay? So this, it's a complicated proof that we won't do. But if you are into math, and especially cryptography, you're going to need this equation a lot. So how about find this? One way is extended Euclid that says 1, that's the GCD between A and N, has to be AX plus N times Y, and X is then A at minus 1 modulo N. That requires still finding the coefficients X and Y. So this has to be a procedure, just like Euclid. How do you find those coefficients? But once you find them, one of them is the inverse. The other way is to try powers of A. Do these things, A squared, A third, A fourth, all the way. Let's call this set powers of A, right? All those powers. A squared, A third, A fourth, A fifth, so on and so forth. Now this is all modulo N. There is a little magic here that one of these powers, some power, will be 1. That's the magic. I'm asking you to trust me until Friday that this is going to happen if there is an inverse. When you raise it at multiple powers, one of them will give you 1. And then if I know that, what's the inverse? If I get a power that gives me 1, I say the inverse is just the previous power. If V was 127, the inverse of A was A at the power 126, because that times A gives me 1. So let's try this for 5 here. 5 inverse, that's 5 at minus 1, modulo 26. I want to apply this method because I still don't know how to get those coefficients yet. 5 squared is what? Let me show you a cool way of doing this. 25. I'm going to use a little bit the negative values, not just the positive. 25 is who? Negative 1 modulo 26, right? And now if I do squaring again, 5 to the 4th is? It's going to be minus 1 square, right? Because it's the minus 1 from here. Square, that's 1 modulo 26. So I already found the v. 5, the v is 4. That is the power that gives me 1. So who's the inverse? The previous one. 5 at v minus 1. That's 5 to the 3rd modulo 26. I think that is 21. So the way to find the inverse, if there is one, again, if there is no inverse, no matter what you try, never going to get to the inverse because there's no inverse. But if there is one, a very basic way to get the inverse is to just raise up consecutive powers. I skipped 1 power for speed. I knew it's 5 to the 4th, so I didn't do 5 to the 3rd. But if you do 5 to the 3rd, 5 to the 4th, eventually you get a 1. When you get the 1, the previous power is the inverse. You're going to need to think a little bit about those things, and then we can explain them better in class. But that is the required material, except for how to find the inverse here. Now I'm going to take another example, but he's going to start distributing the meters. So I think you have them alphabetical? Yeah. Right, so you're going to have to call some names and see where people are. So what I want to do while the meters get distributed is, how do I modify Euclid to get those coefficients? The principle of Euclid is it goes down from the original problem to a simple problem. That's the same way I want to get those coefficients. Actually, I want to get the coefficients in here at the bottom, and then move them up. So can I get the coefficients here? What times A plus what times B gives me 3, the GCD. What's the x I need to multiply with A and the B with 3 to get the 3? That's very easy, right?
0 and 1.
0 and 1, right? 0 and 1. That was easy. But of course, that's not the x and y for this problem. It's the x and y for the last problem. So I want to obtain the coefficients in the same way I've done the Euclid. Go down to a smaller problem, smaller problem, smaller problem. At the very end, I know how to get the coefficients. The last coefficients are going to be 0, 1. But how do I move from here to here? In here, I need something times A, which is 9, plus something times B, which is 6. To get this, the same GCD, right? The GCD stays at 3. So remember, I can have negative values in here. What do I get here?
X is 1, y is negative 1.
1 is here, and negative 1. But the thing is, you're still doing guessing, right? What I would like to say, if you have it here, how do you get it mechanically here? It's a formula that if you solve this problem, x and y, you get 0, 1. Well, how do you apply it to the previous problem? And in here, I'm going to need something times 51 plus something times 9 to get me what? 3, right? It's always 3. So what can it work in there? What if I put this as 6? Would it work? 6 times 9 is?
Jacob?
And
54. What do I need in here? These x and y's are not unique. I could have put different x and y's and get the same, right? Can anybody find a different x and y here? not minus 1 and 6, some other x and y that do the same. Give me a 3.
Negative 2 and 10.
Negative 2 here? No, because you're just multiplying by 2, you get the 6, right? Is there any other additional x and y that will do the trick? Let me help him a little bit. You guys figure this out. Give me a
Negative
stack
2
here.
and 11.
Mix that back. Thank you. Jonathan Crowley. Jonathan. There's another Jonathan. Where is it? Jonathan? Great Daniel. Jacob Davis. Summit D.
No, it's not. It's not how it is. I put this line, sign it, and the one place, that's the way I do it.
No, it's like implied. He's just not, he's making something, but not drawing.
I just heard a lot. How many points I can put my here because I want to because I know I use here anyway. I was supposed to use strong
I think if you use mod, it has to be everywhere.
The only way that I started drawing out
Yeah.
1 to 200, and I found
What you're saying is that he talks about the multiplicative inverse, but in inverse
that.
and when he says the inverse of 5, I just want to say 1/5.
Espinoza.
wrong at all.
Why? So there, yeah, yes, 1/5.
Espinoza. Miranda.
But otherwise, did you still show the correct?
Well, I'm going to be late for the open presentation. Well, I'm gonna, if I have to go find my fellow, I'm gonna be like 10% of my grade for not showing up. I was late. I really hope that you find your fellow. I'm gonna like walk up to her and like wave at her. And then I'm probably gonna turn around and leave.
I used to read the whole thing, right?
So I think it's like
I get out and be like, I'm not
So I'm gonna go wave to her and leave. I think if I can like somehow make that work. You know, I thought I had a lot of work to do, but I finished like 10.
Or you initially roll why do you write minus?
I'm also a Matthew. Is that one definitely yours?
That sucks.